Good morning, class. Today we start physics. So motion in one dimension will be our first unit on physics, so unit 2. And the first thing we'll learn about is displacement and velocity. So we'll go through that briefly here today. All right. Before you start a physics problem, you need to determine your frame of reference. So we're going to watch this old video. It gives a good background on what we mean by frame of reference.
We're used to seeing things from a particular point of view. That is, from a particular frame of reference. And things look different to us under different circumstances. At the moment, things look You look peculiar. You're upside down. No, you're the one that's upside down. No, you're upside down. No, I'm not. He's the one that's upside down, isn't he? Well, let's toss for it. All right. Okay. You lose. He's the one that's really upside down. You better come into my frame of reference now. My frame of reference was inverted from what it usually is. That view of things would be normal for me if I normally walked on my hands. This represents a frame of reference. Just 3 rods stuck together so that each is at right angles to the other 2. Now I'm going to move in this direction. You see the frame at the same spot on your screen, but you know I'm moving this way because you see the wall moving this way behind me. But how do you know that I'm not standing still and the wall moving? It was the wall that was moving. Now the wall has disappeared, and you have no way of telling whether I am moving or not. But now you know that I'm moving. The point of this is that all motion is relative. In both cases, I was moving relative to the wall, and the wall was moving relative to me. All motion is relative, but we tend to think of one thing as being fixed and the other thing as being moving. We usually think of the earth as fixed, and walls are usually fixed to the earth, so perhaps you were surprised the first time when it was the wall that was moving and not Dr. Hume. A frame of reference fixed to the earth is the most common frame of reference in which to observe the motion of other things.
All right, so that gives a good overview of what a frame of reference is, and it touches on the confusing part. So we often think of motion as some velocity or movement relative to the earth. And that makes the assumption that the earth is stationary. So that works well, but the reality is the earth is not stationary. So the earth is moving on its own as well. So it's spinning around and it's orbiting the sun. And not only that, but our solar system is moving around, it's orbiting the center of the Milky Way galaxy, and the Milky Way galaxy is spreading out as part of the Big Bang. You start looking at all these factors, and suddenly nothing is stationary, and everything is moving, and actually moving relatively quickly. So does that mean that all motion formulas need to account for all of this crazy motion? And the answer is no. We can still watch motion relative to the Earth. And that is how we can simplify a physics problem to make it easier. So that's the whole goal of frames of reference, is it's a way to simplify a physics problem to make a simpler physics problem to solve. So the example I always use is the train. So if I am inside a train and I want to throw my little racquetball to another passenger, the question is, do I care about the speed of the train? Now, if I'm just throwing it to another passenger within the train and all the windows are closed, then no, I do not care about the speed of the train because me, the ball, and the other passenger are all traveling the same speed, so we are in the same frame of reference. So if I choose a frame of reference of inside the train, then I can calculate my problem and solve that problem very easily. Now, what if I want to throw that racquetball out of the train and hit a sign on the side of the tracks? Do I care about the speed of the train now? And the answer is yes. So now I have to enlarge my frame of reference and open it up to maybe the Earth's frame of reference. Now I would need to know the speed of the train, I would need to know the location of the sign, and those things would all have to work together. Now let's open that up even more. What if I'm going to throw my racquetball not to hit a sign, but to try to throw it all the way to the moon? So unrealistic, yes, but stay with me. If I'm throwing it all the way to the moon, do I need to enlarge that frame of reference even farther? And the answer is yes. Now I need to account for the motion of the Earth and the motion of the moon around the Earth. I would need a much larger, probably solar system sized frame of reference. So you're going to pick a frame of reference that makes your problem easier. So if you're inside the train, you can pick a very small frame of reference. If you're in this classroom, you could pick the Earth's frame of reference. And if I'm trying to toss the ball to you within this room, I don't care about the speed of the Earth. It does not bother me because we're all moving at the same speed together. So you can have a smaller frame of reference. All right, just something you need to know before we start moving on to motion formulas. All right, so all motion is relative motion. We just discussed that. There is no actual fixed thing. So we only care about the motion of one object relative to another. And a frame of reference is a system of objects that are not moving with respect to one another. And we're going to choose the simplest one possible. All right, the way I'm going to do this is, if you want to write that down, you should pause it now. And I'm going to keep moving to make the video as brief as possible. All right. No Marty challenge this year because I'm not in school today. So we'll have to save that for another time. If we are talking about motion, we first have to know the difference between a scalar and a vector. A scalar is usually what we use in common everyday language. So 5 kilometers, that's a scalar. 125 pounds, that's a scalar. 12 seconds, that's a scalar. So fully defined by the magnitude, and the magnitude is just that number there. So that's your scalar, that's just magnitude only. A vector is when you get direction added onto that. So in math, scalars look something like this, and a vector would have direction, so it would look different, correct? So 5 kilometers east, that would be a vector because we have added direction. So we're going to do this to many, many things in motion because we care about which direction these things are going in. It matters. So we'll see that a couple times today and more throughout the entire unit. One thing to be wary of, sometimes we use positive and negative for directions. East doesn't really work well in a formula. So usually we convert east to just a sign, positive or negative. And you'll see that as we go through. All right, our first scalar and vector combo here is distance and displacement. Distance is probably what you are used to using in normal language. So that would be the 5 kilometers, the 1 mile, the 6 feet, 2 inches. Those are all distances, so they are scalar values. There is no direction involved in any of these, and that's just going to be the length of a path between two objects. Displacement is very different. So a displacement is the change in position of an object. So we'll see in a second that definite has a direction to it. And I'm going to take you through this formula because this is important. This is called a delta signal. A delta in physics means a change in. So delta x means a change in x. xf is going to be your position final. So x position final. Should put x up here because that x denotes x position. And this is x position initial. All right, so say I'm on a number line. And I go from, let's lay out the number line first. All right, say I go from 2 to 5, and say this is meters. So I go from a position of 2 meters to a position of 5 meters. So my displacement, my delta x, will be delta x equals x final. So my final position was 5. Minus x initial, my initial position was 2. So my delta x would be positive 3 meters. So I moved 3 meters in the positive direction. So that is my delta x. Distance is going to look a bit different. It doesn't really care which way you moved. It just cares how far you moved. All right, let's see some examples. So here's our example 1. Now say you moved on this path. So that's rather nice. You went for a nice stroll. Your distance would be the complete length of that line. So say the length of that line is you traveled 8 meters when walking this path. So that's wonderful. That's your distance. Now, it doesn't care about direction. Your direction is ever changing here, and it does not matter. But if somebody asked, what was your change in position from A to B? Now, that is a straight line path, and it's vectorized, so it is pointing from A to B. Now, this is how we care about things in physics. It makes things simpler. So your displacement here, let's create a number. Let's give a little compass signs here to orient ourselves. North, south, east, and west. What was our change in position from A to B? Well, we went east. We know that. And we went a smaller distance or a smaller magnitude than 8 meters. So say, I'll make up a number here, 6.2 meters east. That would be our actual change in displacement. All right, let's look at another one. What if we were to walk around a block? So say I started here, I went 1 block north, 1 block east, I guess, 1 block south, 1 block west. What would be my distance traveled? My distance traveled is the length of the path I took, and I actually walked 4 blocks. What would be my displacement? What is my change in position? Well, I started here, and I ended here. So that means my displacement would be 0, because I started and finished in the same location. So that means I have no displacement over this motion. So distance and displacement can be very different things, and we have to just be aware of that. Now we're getting into our next scalar vector set. So speed and velocity. So speed is distance divided by time. We know that distance is a scalar, so that means speed is going to be a scalar. So distance and time are scalars. They have no direction involved with them, so that means speed is a scalar as well. Velocity, on the other hand, has displacement in it, so that's a vector. So if we're inputting a vector here, then we're going to get a vector output. So if we have a displacement, we traveled whatever it was, 10 kilometers east, then your velocity is going to be east, right? So that's going to follow through. So here's our first real formula that we will use often. V average equals delta x, displacement, divided by your change in time. Remember, our delta means a change in, so this is a change in time. That can also be written anytime you have a delta, it's just going to be final minus initial. So that can also be written like this. So speed is just distance over time, whereas velocity is going to be displacement over time. And we'll need to keep track of that as we go through. All right, so let's look at different values of velocity. Velocity is a bit interesting. If you look back on this slide, average velocity occurs over some period of time. So if I were to drive to Boston, Boston is 30 miles north, and it takes me 1 hour, then my velocity average would be 30 miles north in 1 hour. So 30 miles per hour north. Now, did I travel at a speed of 30 miles per hour north that entire time? No. Traveled all kinds of different velocities, but this would be the average velocity over that 1 hour time period. So, sometimes it's important to know the velocity you're traveling at this instant in time, and we often need that in physics. So there are more than one velocity that you may encounter. There's actually going to be 3 that we're going to see all the time. So we're going to have our average velocity, and this is some velocity over a period of time, but you're also going to have some instantaneous velocities. That sounds just like the word spells out. Instantaneous means at this instant. So sometimes we want to know the instantaneous velocity of that car. So you would want to find some initial velocity or some final velocity. So the example I often use, say I went out on the street outside of the school, and I'm in my car, and I started from rest, and then I accelerated up to 60 miles per hour. That's a very simple motion, say it's constant acceleration. Now, what would be my initial VXO velocity? Well, I started from rest, so my initial velocity would be 0 miles per hour. What would be my final velocity? Started from rest, and I went up to 60 miles per hour. Now, I'm going to add a direction here just to make sure this is a velocity. So my initial velocity was 0. My final velocity was 60 miles per hour. But what would be my average velocity over that period of time? It wouldn't be 0. It wouldn't be 60. My average velocity would be 30 miles per hour. So very simple motion, but 3 different velocities really within it. None of these are very tricky, but you have to just kind of know that if you see a velocity within a formula, it could be any of these. So that's important to know. All right, just some nomenclature stuff here. VXO is initial velocity, and Vx is final velocity. Initial and final are, it sounds like the start of motion and the finish of motion, but it can be any 2 points in motion. You could start your initial velocity at 2 seconds and final could be at 8 seconds, and it's whatever you pick really. But what this nomenclature means is your velocity in the x-axis at a time of 0. So that is your initial velocity. Your velocity in the x-axis at a time of 0. And your final velocity would just be the velocity in the x-axis at a later point in time. Okay? So that's just kind of a nomenclature thing. Vxo is initial velocity. That's velocity x at a time of 0. And Vx is final velocity. All right, what do these look like in practice? Let's start with a simple one. During a foot race, Todd runs 625 meters due east in 85.5 seconds. Just grabbing a calculator here. What is Todd's average velocity? So the first thing you do is going to be a process to solving physics problems. 3 steps really. The first step is to list your givens. Step 2 is to provide some sort of formula. And step 3 is to actually solve that problem. Now, every physics problem we do all year, you're going to do in that 3 steps. Okay? So what are our givens in this problem? It's important to be able to read a word problem and pull out the given information. So we have 625 meters due east. What is that? That is our displacement. Now we have 85.5 seconds. That's our time. And the last thing that you also want to include is what you're looking for. So we are looking for V average. That's our unknown. You want to identify that within your givens. This is the hard part. If you can get good at listing givens, you will do very well in this class. This is the hard part. Now, the easy part, you look at this given information and you say, do I have a formula that has these 3 things in it and I can solve for V average? And the answer is yes. We got really 2 formulas right now. It's not hard to pick the one we want. So V average equals delta x over delta t. Okay, beautiful. Now you're going to solve that. So you're going to plug this given information into this formula. So V average, we don't know. So we'll keep that as unknown. Delta x we do, and we'll plug in that information, 625 meters east. Delta t we know, 85.5 seconds. So we can get our V average. Let's plug it into the old calculator here. We get 7.31. Now, the first thing you need to do, we took 2 numbers and we divided them. So we need to pay attention to sig figs when we do that. This first one has 3 sig figs. This bottom one has 3 sig figs. Our answer has to have 3 sig figs. So I have done that correctly and I've rounded that to 3 sig figs. The next thing we need is a unit. If you look here, this will give you the unit, meters per second. And then since it's a velocity, we need this direction as well. So Todd, in this foot race, traveled at 7.31 meters per second east. Beautiful. Put that in a box. You are done, and that's your final answer. All right, let's look at a more complex problem. Another race. We got a marathon. During a marathon, a runner passes mile marker 18 after 2.26 hours. The same runner passes mile marker 24 after 3.12 hours. What is the runner's average velocity in miles per hour over this period of the race? So, the easiest given to pull out of this is the unknown. So we are looking for V average. All right? So that's our unknown. That's what we're looking for. Now, I would normally be looking for delta X and delta T. But is mile marker 18 a delta X? It is not. That is a position, right? So that is his initial position. It's not a delta X, it's an initial position. That's an XI. So XI equals 18 mile. So if I have XI, do I have final position? Yes, mile marker 24. So 24 mile. That's my final position. What is this 2.26 hours? Well, that's the time on the clock at the initial position. So that's your initial time, 2.26 hours. Your final time would be 3.12 hours. All right, so normally we would just be looking at this formula. V average equals delta X over delta T. But we don't have delta X and delta T yet. So we need those formulas as well. So delta X. Anytime you have a delta anything, it's going to be final minus initial. So final position minus initial position. That will give us delta X. Delta T we will get by doing delta T, which means T final minus T initial. These two formulas will let us solve for delta X and delta T. So let's do that first, because you can't do this until we have delta X, delta T. So delta X is going to be 24 minus 18. So my delta X is going to be a positive 6 miles. So during that period of motion, this runner ran 6 miles in the positive direction. Beautiful. How long did that take them to do? Well, we'll do T final, so 3.12 hours minus T initial, 2.26 hours. Gets us a delta T of what? .86 hours. All right, now that we have these two things, we can plug those right in here. So we don't know V average, but that's what we want. We do know delta X now, so our delta X is positive 6 miles. We know delta T, 0.86 hours. So we get a V average of 6 divided by 0.86. Now I want to go over one thing that I did here that I kind of skipped over, but I want to make sure you see it. 24 minus 18, we have done some sort of math with measured numbers. So that means I need to pay attention to sig figs. So these are both good to the ones column. So we went from 2 sig figs down to 1, but that's okay because it follows the correct rules. Right? Ones column, we have to round this to the ones column, which is what I did. Here we're good to the hundredths column and hundredths column, so our answer is rounded to the hundredths column. Beautiful. When we come over here, it seems like we lost some information, but really just our formulas or our math made us lose seemingly some sig figs. Now we have 1 sig fig divided by 2 sig fig. That means our answer has to be 1 sig fig. So 6 divided by 0.86 is 6.9767, blah, blah, blah. we're going to round that to 1 sig fig, which is going to be 7. So our velocity is a plus 7 miles per hour. And I know it's miles per hour because that's what I input, miles per hour. That is your final answer. Ready to rock and roll. All right? A little confusing. This is about as hard as you can make a standard velocity problem though. So they're not that bad. You just kind of have to pay attention to what you're doing. All right. Have a good day.